Hello, everybody. Thank you so much for joining us today. We are so excited to jump into simple sensor experiments to start the school year. Try saying that 10 times fast. As folks get settled in, I'd love to invite you to grab some water, get comfortable. We've got an hour presentation set aside for you today. While you're getting ready, I do just want to let you know that we will be answering questions in the chat today. So if you look at your Zoom window, on the bottom of the Zoom window, right close to, let me see, yeah, very close to that, the bottom, it might say share for you, I'm not sure, but you will see what looks like a chat bubble. If you click that chat bubble, it'll pull up a chat box, and that's where we will ask our questions. I want to direct you to the bottom of that chat box. You'll see a little two and then a blue button where you can click hosts and panelists or everyone or even maybe specific attendees. What I'd love to encourage you to do is go ahead and click that blue button and set it to everyone. We ask that when you're asking questions today, go ahead and make sure that question is set to everyone. We ask that for two reasons. One, it is information sharing. Somebody might be wondering the same thing. You're helping other people by showing it's okay to have questions. We love to answer them. And also, we don't want to look like we're talking to ourselves. So please set your chat to everyone, and that way we make sense when we're answering your question. Now, to practice this skill, go ahead and in that chat box, let us know when are your students coming back to school. I know a lot of us are in the preparation part of the school year. Maybe we're at the way tail end of the summer, but I'd love to know. All right, we've already got people in the chat. Let's see. Oh my gosh, we've got someone from Peru here. Very cool. And Long Island, lest we forget. Looks like some students are back August 19th, September 2nd, Thursday. Lisa, you got this. Yesterday for Julia, August 13th. Oh, an Italian is in the room. Day after Labor Day in Washington. Very nice. Julian has 2 weeks. Jamie says their students came back yesterday. Happy second day of school. September 2nd, okay. Nebraska, students August 15th, August 20th, 25th, 13th, another 12th. Wow. So all of you are really in the planning period. I can't even keep up. 13th, 18th. The 14th. Okay. Well, congratulations on the last few weeks of summer. I hope it's been restful. I'm so excited to have you all here. We're 2 minutes past the hour, and I want to give our amazing presenters all the time today because we have some really cool experiments to go over. Before we hop in, I'll just share some housekeeping items. If we could go to the next slide. All right, so you will get a recording of today's presentation. It usually takes us about 3 to 5 business days to edit that video, but as soon as it's ready, we will put it on both our website and our YouTube channel. You're also going to receive an email as soon as it's ready with a link to that video, so you can come back and watch this. In that email, you're also going to get a link to the resources folder. Inside that folder, you can see today's presentation with clickable links. We've got experiment files. I dropped a certificate of attendance in there, so there's lots of goodies. As soon as I'm done talking, I'm going to mute myself and drop the link in the chat, so keep an eye out for that. As I said before, please put your questions in the chat box. We would love to answer them. Just make sure you're sending your question to everyone and not just us. And if we happen to miss your question or if you think of one later, please reach out to us. We are here to help. You can email us at support@vernier.com. That being said, I think that's my piece today. So I will hand you off to today's presenters and stick around. We're doing a giveaway at the end, so you have to be on here to win. So I'll see you at the end of the webinar. Thanks, y'all.
Thanks, Dylan. Hi, everybody. My name is Cassie Whitecotton. I am a STEM educator. I currently teach chemistry, physics, anatomy and physiology, and also FIRST robotics. I'm excited to be here with you today. We're going to do some great, small, quick experiments with some great sensors. So thank you for being here. We're excited.
Hi, everyone. My name is Nüs Hisim. I taught chemistry and physics in Maryland for 34 years. Came to Vernier in 2016, and this is one of my favorite things to do is to share some Vernier information with teachers around the country and around the world. And see, we have some international folks with us. And we're looking forward to sharing a few experiments with you and some ideas. And by all means, I'm a tech support specialist here at Vernier. And so if you have any questions, drop those in the chat. Or like Dylan said, you can write to us at support@vernier.com. So Cassie's going to start.
All right, just to share a couple of things with you guys. We are here, we are teachers, and we're for you teachers as well. So we're a very big teacher community driven. So just know that everything that we do today has been done in the classroom, and that's really important for you to know. All the sensors we can use today or are going to use work by 2 modes, USB or Bluetooth. You may see us do both, just kind of depending on how things go. And they can be used on lots of devices, your computer, Chromebooks, tablets, LabQuest 2s and 3s. I'm going to be using my personal computer for school, but then I use these also with my students on their Chromebooks. They also, if you have the newer TI Inspire CX2 Pythons, these connect Bluetooth with that Bluetooth adapter for those. Today's hands-on activities will be using the graphical analysis app. I'm going to use the Chrome extension, which is what my kids use since we use Chromebooks. You can download it for free right now. And then also there's a link in here for the temporary license if you would like to try the pro version. No sensors are required to use the software, so you don't have to worry about that. And you can compare the free and pro versions via the link here that kind of puts everything side by side so you can see the difference. I use the free version.
Software you can do manual graphing in the software. So if you just access the software, there's an option for putting in your data and getting a graph.
So if you have a temperature probe, a standard one, and you're just taking points, they can plot those points as well. And again, we'll have a folder for you with all the shared files on some of the experiments we do today and extras as well. So this is today's agenda. We're going to first start out with the temperature experiment. I'm going to take care of that one that I do with my chemistry kids, IPC, or even middle grade kids. And then Nüs is going to cover Boyle's law, which is pressure versus volume. And that is not a time data collection. It's going to be points with entry. And then we'll switch back to me. I'm going to cover the motion detector, which is really used in a lot of physical sciences and physics as well. Nüs is going to cover oxygen and gas. And then we're going to tag team force and acceleration at the end. We're going to go through setup, talking about predictions, live data collection. So you'll see that. So kind of what we do on live mode when I do it with kids, and also what I see in the classroom. Expectations of data collection. So if you have anything to add, this is a conversation. So make sure, you chime in there in the chat. Also, again, we'll have those files for you at the end in that folder. All right, this is just a brief overview with the sensors to start your year. I have the temperature probes. I have about 8 of them. I just got a few new ones for this year because this is a common probe that we use. Again, the motion detector, that's what this looks like. These are the new ones. I still have the old ones too that have the flipper up and down. Nüs again is going to cover the Go Direct oxygen sensor, gas sensor, and the force probe. Did I miss anything? I think we're good. All right. So I'm up first. Yay. Yay. So I'm going to show you guys how to connect these first, because that's always a big question is when you're getting started data collection is what do I do and how do I do this? I'm going to use the Google Chrome app. Like I said, I'll show you how that works. But when I do this with high school and middle school kids, when they're coming to me, especially in high school and chemistry, it's the first time they've ever done data collection. Our biology doesn't really cover that a whole lot. So I like to put this in their hands first because it's low risk, it's high success rate for students. It's easy for me to set up. There's not a whole lot that they have to do with it. I don't have to pull out a bunch of materials. I ain't got time for that. So I have 4 preps and I am usually running full steam ahead. And when I do this, I give students clear instructions, but also we talk about investigation kind of towards the end. So let me get out of the presentation here, and we're going to go to Google. So you just simply type in the graphical analysis.app. And this is what it looks like when it pops up. You'll get this prompt, and I'm going to turn in my temperature probe sensor, and I should get a nice little light that's flashing. I don't know if you can see that. There it goes. And we're going to click on sensor data, and we're going to go to wireless. And it should pop up here that it's connecting that Bluetooth connection, and TMP is temperature. And this is a number, identification number on the probe itself. On the very back, there's a USB. I know that's really small. So they're going to look for the last 2 digits of that number to pair them. And hopefully it pairs. Yay. And it says done. Now, if you are choosing to hardwire this, it comes with this cord right here. You would just choose USB, and we may do that later with the motion detector, so you know what it looks like. So you can see here, I have got temperature being read, and my time data collection is really long. It's 180 seconds is the default. So in order to change that, I can go down here to time-based mode, and I can set the time that I want kids to collect data for. I prefer 10 seconds. It can be longer. It's whatever you choose, but I'm going to do simple math with my kids because we're dusting off those cobwebs, and maybe they haven't done algebra all summer. They've been TikToking and Fortniting and doing what kids do. So in the lab that I like to introduce kids with data collection is I give them 3 basic experiments, basically. And the first one is that they have to create a temperature graph that has a linear positive rate of change. Okay, so they can make predictions in here. Let me get back to it. Come on. Oops.
The next tab over.
Yeah, my Zoom menu is wanting to pop up.
I hear
Technology
you.
these days. So I want them to make a prediction about what does that look like in their head. They can do it in their graphing notebooks or however you choose as a teacher, but they can do it on the software too. So there's these little dots down here that they click on and see where it says add prediction. They can click on that, and the condition was it had to be linear and positive. So they can make an attempt to draw a line of what that might look like. Now, obviously, I said over 10 seconds, so I'd want their prediction to be over the full 10 seconds, but you kind of get the idea here just for time's sake. Then in order to collect data, we're going to do that. We're going to collect some data. So all they do is they hit collect, and they kind of can talk about how they want to do that. How are you going to increase the temperature? Make sure you tell them not to stick it in any bodily orifices, not their mouth, their ears, their noses, and other places. But they can use their hands. They can use a towel. They like to create friction. So when they do that, I'm just using the palm of my hand. They can see that that rate of change is pretty linear. And just by adding the friction to the end of the probe. Now, the temperature probe, the sensor's in the end of it. So that's why they'll find out they do this. It doesn't work that well. So adding friction to the end, they get better results. I would have them then calculate the rate of change by hand and take where they started. So if they click on the graph, they can get that beginning point, and then they can click on the end point over here. And see if I can get there real quick with all my windows open. They can click over here and do that mental math. Dividing it by 10 is quick and easy for them, hopefully, to move a decimal place. So, and then they can run a regression. And compare up here, you'll see that I got the slope as 0.41. And what does that mean? So we're dusting off those cobwebs of what is slope, what is a rate of change, what is my starting point, my initial point. And you can work through with the kids of y equals mx plus b. Well, what does that look like in form of equation? Just to get them back going again. And I give them 3 scenarios. They have to recreate it doing a decrease in temperature, but it's linear. They have to then do a non-linear one, which is also positive, and they could do a negative one as well. So then I bring fun little things like a hair dryer where they can heat up the temperature probe with the hair dryer to see what that looks like on hot or high or cold or whichever they choose, and they can see those curves. I provide them ice and ice water so they can cool the temperature to see what the cooling weight is. And then I also give them option of evaporation of alcohol. We don't talk about the chemistry mechanics of the evaporation, but we talk about the mathematics and what does that look like, to get used to using a probe, reconnecting it, starting new experiments, that kind of thing. So like I said, it's pretty easy to get started with the temperature probe. It's one of my favorites. Oh, hit the wrong button. To navigate in the classroom, and you don't have to have a whole lot of equipment. That's my thing. Less is more in these days. So, all right. Temperature probe, easy peasy. And then also with this one, there's a really cool experiment that Vernier has. It's called Hot Hands, that kids can do. These are some example graphs, where you can give them 1 temperature probe or 2, and they look at the heating rate of each hand. And why would that be? Why would they be different? Is usually an investigative question. Is it different per person, or does hand size matter? Those types of things. So this is something that we do in anatomy. We look at surface area of the hands, size, blood volume. Does that make a difference? So hope you all enjoyed that.
All right. Starting to answer questions in the chat. So let me grab the screen here and we'll look at another sensor. Sorry, we're giving you guys the bums rush a little bit here. The issue is that we have just a limited amount of time, and we're going to try to get as much in here as we can. And unfortunately, we're probably not going to hit everything you guys you might want to see, but we also want to get you going early. And so what Cassie just did is she did a data collection against time. And a very common question that I get from phone calls and emails from customers is, hey, can I collect data against something other than time? And so I was thinking, like, what can we do that you might do relatively early in the year? Gas loss may come up relatively early in the year. So what I'm going to do is I'm going to do a reaction, same using graphical analysis. Let me make it a little bigger so you guys can see it a little bit more easily. But I'm going to use a gas pressure sensor, and I'm going to do what's called an events with entry data collection. So I'm going to use the GoDirect. We get a lot of, I saw a bunch of questions in the chat. Can I use the LabQuest? Can I use the wired sensors? Absolutely. But we want you to buy new sensors. So I'm not a great salesperson, as you might be able to tell. So as Cassie pointed out, sensors come with a cable, a USB cable. This serves 2 purposes. You can collect data through it. You can plug it in. Every GoDirect sensor has a micro USB port, and you can collect data straight into the USB port on a computer or a Chromebook. You can also collect data wirelessly, and that's what we've been trying to impress you with. So that's what I'm going to try to do. I'm going to power this up. Every GoDirect sensor has a radio built in. And so what it's doing is it's transmitting right now. If you were in your classroom, this is the choice, right? If I plugged it in by USB, I would choose that, but I'm going to use wireless. If you were in your classroom, you might have a bunch of these, popping up. How do you know which one is yours? There's, as Cassie pointed out, there's an ID number on every single one of them. So what you're going to want to do is find that. This one ends in B8, which is this one right here, and then just connect to it. I had a customer today with Chromebooks, older Chromebooks, and she was having trouble getting connected. Yeah, it depends. We have some school districts that even have turned off Bluetooth, and so plug it in. That's going to be your only option. Now, if you look at the screen, you'll notice that it says 0 to 900 seconds. Boyle's law is the relationship of pressure and volume. Time's not involved. We need to change this so that we can do a data collection against volume. So bottom left corner of the screen is the mode menu that Cassie used earlier to change the time duration for her experiment. I'm going to change the mode of data collection to what's called events with entry. My event is going to be the volume of the gas. And I am a bit of a unit Nazi. And with gases, I prefer cc's. With liquids, I like milliliters, but we did write the experiment to match the syringe, and because that's what the syringe is marked as. So I'm going to go ahead and be consistent, even though in my classroom I would have all the files that when you buy a lab manual from us, all the files you get come in Word format. So I changed every last one of these, especially for AP. I've done AP for 25 years. And I changed every one of them so they matched the way I wanted to teach. And so what we're going to do now is you'll notice that we have a slightly different menu for starting data collection. I'm going to hit collect because there is no anxiety, none. It's waiting for me to tell it when to take a data point. So I'm going to take the syringe and I'm going to put 10 milliliters of air in it. So now I have 10 milliliters of air. By the way, the pressure sensor comes with a little baggie of all kinds of goodies. Do not put this out. You're not going to get it back this way. There's all sorts of yummy goodness in here, especially the little ratchet clamps in there that the biology teacher wants for respiration. In my school, these all went in a plastic shoebox. And then what we did is we just pull out the one thing you need for the experiment. For this experiment, all you need is the pressure sensor, pardon me, the syringe. So what a nice, easy setup. Okay. Now, what we're going to do is we've got 10 milliliters of air in here. And so I'm going to hit keep. And it says, well, what's the volume? Well, believe it or not, it's a little more than that. Inside the pressure sensor, there's a little bit of extra volume associated with the connection. It's about 0.8 milliliters. So I'm going to add that in. You might have your students actually discover, if you don't put in the 0.8, it doesn't come out as quite as good. And with our short time, when I do a regular training, I try to do it the wrong way just so that people can see, what happens. I'm going to compress this. This is a great two-person experiment. I'm going to compress this to 5. I'm watching the meter until it stabilizes. It'll probably never stop. And so I'm going to hit keep. Now I can relax because it grabbed the pressure and it's asking me for the volume. Well, I had it at 5, but remember there's that 0.8 milliliters I have to account for. Let's go to the other end of the syringe. I'll go up to 20. Let's see, there we go, 20. Watching the pressure, and then I'm going to keep that, and I have 20.8 milliliters of air. And then I'm going to go down by 3s, mostly to save time. You could do whatever you want in your classroom. So let me go down to 17. And then, oops, I forgot to, let me keep that point. It's okay because it already got the pressure from that other one. So let's see. Yeah, yeah, we're good. So now we're at 17. The pressure is stabilized. Keep 17.8. If I screw up, yell at me. Okay. I'm not paying attention to the chat right now, guys. So if there's a question comes up, Dylan or Cassie, if you can't answer it, just hang on to it and I'll try to get to it a little bit later. I'm going down by 3s, sort of by 3s. I went down to 15 that time, so not exactly. It doesn't matter. You can even do them in any order you want. There's no rule. I'm an old bugger, so I'm gonna want to kind of do it in some sort of order here. But you don't have to. You can do it in any order you want. In the Vernier world, you cannot change data that's collected by a sensor, but you can change data you put in. So if a student made a mistake, they could go in after data collection and they could go in and they could modify a value. They cannot modify the value that is collected by the sensor. So it's something to be aware of. Once you're done, you hit stop, and then Mr. Hisim, I still have more data to collect. You could hit collect. Unfortunately, if they need to add data, there's this word that a lot of students don't know. And then there's this big green button that says, pick me, and it, they're gonna hit the wrong one probably. But you can add data to a data set. If you need to. If you're doing an acid-base titration, the process would be identical to this. All right, so what's the relationship? At this point, you can do all the analysis you need right in the app. So the file that Dylan shared with you guys, it tells you exactly how to do this. Bottom left corner is this little graph options dude, and you can pick curve fit. Cassie used the linear fit. That's the most common one, so it comes up by default, but there's all kinds of other choices. You can either let your students explore what's proportional. Well, that doesn't fit the points. What's quadratic? Oh, that's sort of kind of. Let's see, power fit. Ooh, that's looking pretty good. Inverse fit. Yeah, it's also looking pretty good. Depends on the level of your students. Okay, I kind of like the power fit because pressure is inversely proportional. We know this. The students are going to discover this. And so let them go ahead and do that. And you'll notice that not horrible. Negative P is inversely proportional to V. And so it's V raised to the negative 1.021 with my data. Not uncommon is, especially physics teachers, wanting to be able to linearize the data to find a y equal, a linear regression relationship in which there's a slope that you can use. In this case, that would be nice to know so you could find the constant that turns pressure is inversely proportional to volume. What's the value for K, right? It's equal to K over V. And so built right into graphical analysis is the ability to manipulate your data. You can export this data to Excel or Sheets if you want to, or you can just click on the three dots next to the column you want to manipulate, add a calculated column. I want that column to be the inverse volume. And like I said, I'm a bit of a unit Nazi, so I would want the students to put in their 1/ml by type. And then I need to tell the software what to do. So I click insert expression and I try to find something here that's going to match. Well, there A over X. A and B are constants, X is a variable. And so I would click on that. And so I have 1 over the volume. If for some reason the students picked the wrong column, they could pick whatever variable they wanted. But this is, since I chose volume, we're good. And so now I can go and I can plot that. It doesn't automatically do it, but what I can do is I can switch the x-axis to inverse volume, and woo, baby, that kind of looks linear. Let's find out how linear it is. So I'm going to pick, this time I will do a linear curve fit under putting a curve fit on it. Wow, Nüs, 3 nines correlation. This value, the best it can ever be is 1. And so 3 nines, I said 4 nines, that's even better. So very good curve fit, even though I was doing this left-handed and talking with you all. And then of course, the slope is the value of K. So if you're having your students write an expression for the relationship between pressure and volume, then in this case, 1122 would be the value of K. Notice the units are there too. We have experiments in our lab manuals for all the gas laws. So we have experiments for Gay-Lussac, we have experiments for Charles, we have experiments, this is Boyle's, and also Avogadro. In fact, I did all 4 gas laws. I don't know, Dylan, was like 2-3 months ago, and I did them all in an hour. And my value for absolute zero from Charles Law wasn't horrible. It was pretty good. And so will holding the syringe by the hand, wrapping your hand around it, increase the pressure measurably? It will. If you warm up the gas, it will definitely do that. So it's probably better not to wrap your hand around the volume because yeah, you will have an increase because of the change in. And remember, with Boyle's law, we're assuming that the temperature is constant and the number of molecules is constant. So if you're heating that up with your hand, then you're changing one of the variables there. So let me quickly look over this. Love the coffee ideal, such as investing. Okay, let's see here. Will holding syringe. Not that I've seen that. Yeah, it will actually. If I hear, let me take the syringe and I'm going to hold it with my hand. Watch the pressure. You see the pressure's going up because I'm heating up the gas in the syringe. So, okay. Gazapalooza. I like that, Chris. Thank you. I'm going to steal that one. Okay. All right. I think I've hit it all. Let me go back and make sure that I didn't miss something. And so, yeah, we just did a little data collection, and now it's Cassie's turn to tell us about the motion detector. So go for it, Cassie.
All right, guys. Nüs, are you going to quit sharing or you want me to
Yeah, I'm
share?
sorry. I'm being
Okay.
There
I
you
just
go.
want to make sure I get back to where we need to be here.
Yep.
Okay. There we go. Yay. So motion detectors are classic in IPC or your middle grades, and then also in physics. So we use this one a lot. My physics kids, I'm in a very small school, so I saw them last year for chemistry. I have them this year for physics. So they already know how to use the temperature probe, but we do review just connecting a sensor, plugging it in, getting some data, writing about it, and then it gets all those cobwebs off because we use this one a lot. I don't want to have to fight those mechanics when we're doing data collection by the time we get to actually use a motion detector. So when we do this one, I'm going to start sensor data collection. And if you notice here, when I did this, it automatically detected a temperature probe. And that's because I didn't disconnect it. My temperature probe is still flashing a green light. That means it's connected. So I have to go down here in the bottom right. There's a little, it looks like a little spoon almost. I can click on disconnect and it will disconnect any sensors that are currently connected. And connect my motion detector. We're going to try this wirelessly. Hopefully it works. Oh, look, there it is. Again, I can double check that number on here. That's important because if you have 8 of these going, you don't want them to connect to somebody else's. So we're going to connect. I should get a green light. And I don't know if y'all can hear that, but it makes a ticking sound. So if you have the ones that plug in directly, the old flipper ones, I don't know what to call those ones that flip, they make that same ticking sound. Now, important thing about this, when it sends this out, when I start my data collection, the sonar wave comes out as a cone. So it radiates outward and it's about, I would say about 3 to 3.5 meters wide when that data collection starts. So it's going to pick up some noise if you're doing like match me with your students or something of that sort and their arms are walking. Your band kids are always the best at this because they can roll their feet and they don't move their arms a lot. I like the Bluetooth ones because the kids can hold them and walk with them. And I give them the same scenarios that we did with the temperature probe as review, but we're going deeper this time and they can hold it and walk it. So they have to create a position versus time graph that is positive and linear rate of change on that. So what does that physically mean if I'm holding my motion detector and I have to have a positive rate of change? So I really focus in on the vocabulary in physics using this, and they have to write about it. So again, I would have them make a prediction. So there was a question about where that is down here in the bottom left, and they're going to add a prediction. The time here is for 5 seconds. It's fine. It could be 3, it could be 10, it could be 20, whatever you want. But I want it to have a positive rate of change. I can do this with my finger. You like how I tilt my head as I move my finger? I just noticed it. There we go. It's a little noisy because I'm not using a mouse. I'm using my finger across my mouse pad. And they could save it. So I have a rule with my kids in science that they have to make a prediction always. They can't collect data until they do this. And I verify it. I don't care if it's wrong. I don't care if it's right. Just think about what's going on. So then if they're going to start collecting data, course, they're going to start here and I'm going to do this or attempt to do it. And I have a stool over here to my far right, so it's going to put it away from me. And I'm going to collect data.
Ooh, nice.
So not bad, not too shabby, all right? So I always tell kids, you know, make sure it's picking you up first. That's that flat area. And when we talk about the motion detector, let's talk about what's really going on. I wanted something that was positive and linear. Well, what does that mean? What did I physically have to do to get that? And what is that starting position? So we start making those connections between what am I physically doing? What does the data tell me? And this is a really easy way to do it. And then I would have them redo the data collection, but just the opposite. Now it has to be positive, but decreasing or a negative slope, right? So we don't have a negative rate of change really, but it's just, what does that sign tell us? And so we're going to try it again. Not so pretty this time.
Not bad.
Not bad, not bad, not bad.
I didn't think
But,
so.
you know, and I would have them redo the prediction. And again, what does it look like if I'm going to increase in speed? So, and I can turn on both graphs here. What's cool about the motion detector is you can see here, I have position, velocity graph, and an acceleration. So it will give you all three. This was my first data set, so I'm going to turn on that one. We could see what time they cross if I were to be moving maybe two people crossing paths. If I turn, I'm going to turn the velocity off on this one. It's pretty noisy, but I'm going to have them calculate that average from the position versus time graph to see what that average is. So it's not ever going to be perfect on the velocity graph. If you use a car, which we'll see later, or spring, it's a little bit better data. Me walking, no. And why is that? Because I have my hands moving, I'm rolling my feet, my head's bobbing. That's why I said your band kids would be really good at this. They usually are. But you can tell that. Okay. Then I'm going to turn, let's see. We're just going to do a third one here. Let's see, maybe if I can get it running. Let's see. Y'all don't laugh if I fall.
No problem. Oh.
Oh, not bad, not bad. You can tell here we got a little bit of a curve, my acceleration. So your competitive kids really get into this because I tell, all right, we're gonna see who's got the best, who's gonna get off that line, you know, football season's here, who's getting off the line first. And so they really like to kind of test their acceleration, get that positive linear, or not positive linear, but positive and increasing graph. And then I let them do their own, right? So maybe this time it's slowing down, or they can use a car and create their own graph. Maybe they're stopping and starting again, or coming towards. And we really bring in that vocabulary using this one. In my old school days, I did match me a lot, but I like giving them the 3 scenarios plus one more, and then we do the math and we write about it, because scientific writing is hard for kids. And position versus time graphs, or your acceleration versus time graphs, and velocity versus time graphs is a really good time to help pull in that vocabulary for physics. We spend a lot of time in mechanics. So I haven't been looking at the chat. Any questions over that? It's, yes, free fall data, yes. That's where this goes, right? In physics, they go into free fall data. They go into Newton's laws. So doing this, I set up all of those lab skills, and then we can focus on the science and some of the other labs to where they just know how to run the sensor. I'm teaching the sensor within these labs and those concepts, and then we can move on, and it's less about the sensor itself. So
Cassie, which age group would use this type of
I've done it all over. I've done it with middle school, because middle school does cover motion and IPC. It's 7th or 8th grade science, depending on where. I've done this exact lab with them, and then I've done it with high schoolers. It works. It's easy. It's not time consuming. I only have 42 minutes, so I have to be very impactful for what I do with my, I guess, sensors, just because we're rolling from day to day very quickly. So yeah, it's very simple, and I love it. It's one of my favorites.
All right, let's do you have more to do?
No, we're good. I'm gonna turn this ticking off.
We'll do a little biology love here before we run out of time.
I know, right?
Yeah.
Let me get back over here.
Yeah.
Oh, there we are.
See if I can share on top of you. I don't know if I can or not.
I think let me stop sharing real quick.
So for for you biology teachers, we were trying to think like what sensors, are biology related that you may use earlier in the year. And it's a little tight, this might not be right at the beginning, but oxygen and CO2 are super common sensors that biology teachers like to use. So, I'm thinking about which one would be relatively easy to show. I'm going to do the enzyme reaction. And so what you see back here on the stir station is yeast cooking. Of course, it's been cooking a while, so hopefully I didn't kill it. Not cooking, but it's cold now. I started out nice and warm. And peroxide. So we're going to do the decomposition of peroxide, and we're going to use yeast as the catalyst for this reaction. And so and you can do this with the pressure sensor, but I already did the pressure sensor. So let's do a different sensor. So I'm going to use the oxygen gas sensor. And this one, the pressure sensor one, test tubes. And the pressure sensor comes with stoppers and tubing and everything you need. I'm going to do it with this O2 sensor just to be different, honestly, just not that you can't do with the pressure sensor. So I'm gonna get the O2 sensor on here. So I'm hitting the power button. It's transmitting. Let's go to graphical. And while Cassie was talking, I went ahead and disconnected my pressure sensor. And so let's see. There it is. O2. Let me make sure that's the right one. 552. That's it. Let me connect to it. Now, one thing I wanted to show you with this. Whoops. Maybe not. My computer maybe not liking Bluetooth right now, and it shouldn't do that, but Bluetooth is Bluetooth. That's why it's nice to be able to connect by USB if that fails. I wanted to show you one more thing here, and that is a lot of these Go Direct sensors also have other sensors built in. For example, this sensor has a temperature probe, so you can access. I'll turn it on just for giggles. So you can access that. And in this experiment, there actually is a part where you do change the temperature of the peroxide so that you can see how that affects the rate at which the peroxide decomposes. So I'll turn it on, even though I don't really need to graph the temperature. So I'm going to turn that graph off. You can have up to 3 graphs showing. I'm just going to show oxygen gas in percent and time. And so we're pretty close to ready with the setup, except that, my gosh, 300 seconds. We're not sitting here for 5 minutes watching this thing go. And so I'm going to quick speed that up. In the lab, it says 180 seconds. For our purposes, I'm going to really make it short. It's just going to be 45 seconds. And in the lab, it says to make the rate 0.25 samples per second. So it's a little bit slow in the data collection, but that's all right. That'll be good for us. And so it's ready to roll. And so now what I'm going to do is I'm going to take five milliliters of just plain old peroxide. Now this peroxide has been sitting out. I don't like storing the peroxide out. We keep it in the refrigerator. We did that at my school. We do it at OMSI, the science museum that I volunteer at. But that's another factor that's going to affect this reaction. So, when you're actually doing this reaction, you probably want to start with your peroxide at room temperature. That's 5 milliliters of peroxide. And I'm only going to do one run just because of time, but you would actually do 3 runs with different amounts of enzyme. So the lab says 5 milliliters of peroxide, 5 milliliters of water. Let's get that in there. And you biology teachers talk among yourselves, because I'm a chemistry teacher. So if I'm screwing something up, you better let me know. And so that's going in there. And so now what I'm going to do is I'm going to get another dropper, because we're going to put this in the bottle comes with it, with the sensor. So I'm going to put that in the bottle. I'm going to give it a little swish. And then in the lab, what you do is you actually do 5, 10, and 20 drops just for the effect. I'm going to do 20 drops. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That was a squirt. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. I think I had a little bit of a squirt there at the end. So I'm going to put in the sensor and I'm watching the oxygen level. Usually I want to see like a little bit of change. But then what I'll do is start hit collect. And Cassie talked about making predictions. This is a perfect experiment, right? You would have the students make a prediction, like if I was doing this with 5 drops or 10 drops, how would the rate of oxygen production be affected? Or the experiment has 3 parts. The part number 2 is temperature. And so you could run this with the peroxide warmed up at different temperatures and see how that affects the rate. And you can also do buffers. So you can see how does the peroxide, pardon me, not the peroxide, the enzyme, how is it affected by pH? And so you can try, a neutral pH, an acid pH, but what's nice, as Cassie had pointed out earlier, you can get a nice rate of the reaction right there. And then that was with 20 drops. So you can say, okay, well, if you want to make it look impressive, I can zoom it in, then it looks a lot more impressive. It's the same graph, but with the scales obviously adjusted. But you can have your students say, okay, if I use 10 drops, I can make a prediction and say, well, it's going to look something like that. My students hated this, by the way. Logger Pro and LabQuest app all have predictions built in, and my students were all just in fear of their lives, right? It was like, well, Mr. Harrison, if we get it wrong, the only way you lose credit is if I don't see a prediction on your graph, right? Then you're going to lose some credit. So yeah, with this experiment, let me look real quickly here. I use the CO2 in the back. Yeah, sure. Yeah, there's very common is to use this sensor and the CO2 sensor simultaneously. I hate getting predictions wrong. I agree, Janelle, but that's the way science works. 99% of the time, science gets them wrong. But yeah, you can use them at the same time. We do sell a bottle that has another hole in it. It's called BioChamber. We have a 250 and a 2000 milliliter bottle. And so you can do things like photosynthesis and respiration for things like spinach leaves or germinating peas or something like that. So you can connect both, collect data for both sensors at the same time. And you'll notice this one's kind of cool. But the CO2 sensor is the same. It has a temperature probe built in, and I actually wrote an ideal gas expression in the forensic chemistry lab manual. Using the CO2 sensor and the temperature probe. And it's in the, like I said, in the forensic chem book. And so let's see, what did I do it right? Did I miss anything, Cassie?
No, I don't think so.
Okay, so let's see. So the last one is back to physics. I don't know. We gave physics a lot of boost in this webinar.
Well, we went for easy. We tried to do
the
easy.
Well, chemistry is the central science. What's physics? There's some kind of a thing about physics, right? That you can't do any science without physics, right? So, all
That's
right.
right.
So what I'm going to do is I am going to do an experiment with the force and acceleration sensor. By the way, if you buy a sensor card from us, these are in there, but the sensor card will also measure position. So that's kind of cute. But this thing can do force and acceleration. Why would you want to do that? Newton's law, right? I mean, that would be the biggie, right? And so let me go back. I'm going to do what Cassie did. I'm going to get rid of the right now the oxygen sensor is still connected, so I need to get rid of that. Otherwise, it just confuses life. And so now the oxygen sensor is disconnected. Let's do a new experiment, and let's connect the force sensor. And Cassie, if I say something wrong, please jump in.
Oh, okay.
Because this is I taught physics like literally decades ago. Okay. And so I could easily say something wrong, and that would not be unusual for Nüs. So I'm connecting my sensor. What happens is when you connect it, the red LED starts flashing green, indicates that it's connected. And for this experiment, I want the force channel, but I also want the acceleration. Check that out. X, Y, and Z acceleration, X, Y, and Z gyro. They've been putting these things on paper plates and using them as controllers with the, I don't know, what's that? You mentioned it.
Fortnite.
Yeah, they use like they program it, right? You can program the sensor. I want the X-axis acceleration because this hook is where, oops, took my hand out of the way. That hook is the force sensor. So I'm gonna turn that on. Let me turn on both um, meters so you guys can see them. And then this sometimes happens when I'm displaying stuff. What I'm going to do is I'm going to put this guy on the table for to start with, and I'm just going to move it back and forth. Now, in the actual experiment for this, you put this. You want to reduce the friction, so you put it on something really low friction, like a cart or something like that. But excuse me, I'm not going to do that. So what I want to do is I want this thing to start out reading 0. So on the little itty bitty meters at the bottom, I can change the units. I can also 0 the sensor. So I'm going to do that for both of these. And so they're going to be pretty close to 0. And then what I'm going to do is I'm going to move the sensor back and forth by just pulling and pushing on the little hook here that's connected to the force probe. And let's collect some data. Pretty ugly, but yeah, it's like you can, let me zoom it up here a little bit and you can kind of see what's going on. It's nice the two graphs are sort of linked to each other. What's really nice to do is to just take those and combine them, right? F and A, let's see, F and A, that would have something to do with second law, wouldn't it? F equals MA. So I'm gonna have one graph. And let me change the time scale to acceleration. Boy, that's ugly, but if you look at the scales, you can see it's like a very small difference. And so I can do a little curve fit on here, and the slope will be the mass of the sensor, right? So according to this, it should be 76 grams. All right, let's find out. Let's see how good that came out. So I'm gonna go and put this on a balance. Oops, can't close. This one's an analytical balance, but I can't close the lid. So I don't know. That wasn't so good. Let's see if we can make friction a little lower. So what I'm going to do is I'm going to grab a spring. So here's a little cushy spring. Let me hook him on here somewhere. And not too good there. Let me see if I can hook it on better. There we go. And then let me hook the force sensor back onto that. So 90 grams, huh? Okay, let's see. What not done well with this, but I'll let you guys, you physicsy folks, figure that part out. Let me get this thing up a little higher. I was using this for another experiment earlier. I was telling Cassie earlier, I've been doing trainings all week, and so I've been robbing from our kit here. All right, so there's the pressure, there's the sensor. Let's let it go up and down, get it kind of level out here a little bit of the ugliness, and then let's collect some data. Oh, let's
Now,
go.
one thing why this is collecting data, I'm going to interrupt you, is important to know that the x-axis on the force sensor is measured in the direction of the hook itself. So kids have to kind of understand that that is how it's set up. It's moving in the Y direction, but it's collecting data in the x-axis relative to the sensor. So when they go to choose their graph or which sensor to turn on, they need to make sure they choose the x-axis acceleration because that's the direction of the hook. You can look at the other ones because it's moving in all three, like vibrating back and forth. But if they want just that hook data, it's the x acceleration.
You could turn off the force and turn on the 3 axes for acceleration and put this thing in your pocket and go on an amusement park ride or something like that. All right, let's see. I didn't zero the sensors. I'm an idiot. Okay, let's try that again. I did not zero the sensor. So the force sensor, I don't know, is it worth zeroing it or just leave it at that? I'll zero it. Let's see what happens. I don't know. Look at it, 9.8. It's jumping around 9.8. That's not so horrible, actually. All right, let's see if I get this thing going again. I'm guessing the slope wouldn't really care, but let's do that. And so nice and smooth looking. So we did kind of take away some friction. And so now let's combine those two. This is kind of nice. Look at that, where the force is the strongest, the acceleration. Isn't that nice? Okay, so let's look at one graph. And let's do force against acceleration. Well, that doesn't look quite as nasty as before. Let's look at that slope. Okay, let's see. Curve fit, linear. Got better. Right? 81.5, 81.6. So it was 90, so I'm off by 10%. Yeah, okay. Not super.
Not bad. Not too bad.
Yeah, well,
Not too bad.
so remind me, do our physics teachers okay with 10% error? Maybe, maybe. So yeah, I'll leave that to you guys. But yeah, just you could do Hooke's law and stuff like that too. Yeah. So anyway, looks like EKG or ECG. Yeah. Let's see, slope better than 100%. Yeah, better than 100% error. That's true. Depends on the class. Yeah, your AP kids may not be happy, but your regular physics kids won't even know, right? So yeah, another option for kind of fiddling around with second law. Of course, if you had two of these, you could do third law. I with two of them, I used to have. Remember, I had told the kids, I'd say, "You stop pulling and you pull," and they were like, "I can't stop pulling." It's like, hey, that's the whole point. Any other last minute thoughts here? We got 5 minutes, and we still need to do a drawing. So I just want to make sure. That we answered the questions, because we're under 5 minutes at this point. Would it have mattered that you zeroed the force sensor when it was hanging? I did zero it. I don't know if you noticed, but I did zero it. So it should be reading close to zero when it's not working. So I did do that. Yeah, because otherwise and the question is, would it have mattered? Should I have left it unzeroed? I don't, I'll leave that to you guys to fiddle with. The problem with the wired force sensor, of course, has got the wire jumping around. And so with physics, the wireless sensors are just, the cat's meow. Where, the wire moving up and down. We had this similar experiment. It was the G experiment, the one where you threw a GI Joe with one of these connecting,
Mm.
and you could get the value of G. But the problem was it was wired, so it was always kind of an annoying thing. So outside,
I want to answer Janelle's question real quick. Just
yeah,
take a
go for
second.
it.
She's asking about writing tasks you suggest for these labs. The more labs that you do, and the more that they write about what they are doing, and the easier it gets. Trying to think on the top of my head, when we do force and Newton's laws, and this whole lab, we don't do this exact one, but we do the Atwood's machine. I actually have them write me a description about that, right? What is going on? Another one that we do is light. So talking about mirrors and lenses, and what do they physically see versus what they predict to see based upon their calculations, or the color, that kind of thing. So the more you can do it, the better and easier it's going to get. Calculated value columns. Yes, unfortunately we didn't get to it, but yes, you can do calculated columns.
Yeah,
And energy. Yeah, energy.
you
We
can
didn't cover
do
energy,
like
but
ball toss, and you can do potential and kinetic energy, and some of the energies, and energy conservation. So yeah, absolutely. There's most common things you could do in Logger Pro, you can do in graphical, and you don't really eat everything that Cassie and I showed you today does not require Pro. So, there are some nice pro features, and if you guys want, there was a code, and you'll get the link to it earlier on if you want to try pro for free. That code is actually good until the end of September, and you can use that with your students. So, by all means, give it a shot. But everything we did today, free. Okay, and if you already own the sensors, free. The only thing I should mention before we go to the drawing is the Lab Pro interface will not work with graphical analysis. So if you have our old wired sensors, you have to have a LabQuest interface for, especially if you have digital sensors. Or a Go link will work as long as your sensors are analogs, like temperature and pH and pressure and things like that. Photo gates and motion detectors require a digital interface, so a LabQuest of some kind, even the original one will work. All right, I'm going to shut up. Dylan, do we have a winner for the Go Direct temp sensor?
We sure do. So as we were in the webinar, I went ahead and entered everyone's names into a random name selector. And today's winner of a Go Direct temperature sensor is going to be Jonathan H. So congratulations, Jonathan.
Yay!
Yes. Uh,
Yay.
I need to get some shipping information from you, so I'm going to email you as soon as we're out of this webinar. Keep an eye out for an email from someone at vernier.com. So I will probably email you in the next 10 minutes. So keep an eye out for that. It might go to your spam, but would love to send you your sensor.
We are here for you. Multiple ways you can get in contact with us. The chat feature on our website is super popular. Also, Cassie is a trendsetter. We are still looking for trendsetters. I think I might have noticed a few possibilities in the chat. On our website, this link down here is a live one. So when you get the slide deck, you can actually, well, just go to our website and search for trendsetters. So if you're interested in becoming one, there's actually a thing on here where you can join the community. So we would love to see more people using our stuff, and we want to do more webinars with our trendsetters, so that you can see that people like you are using this stuff all over the place. Okay, I think I killed all the time, Dylan. Did
You
I?
did it.
I think I
All
did.
right.
All right. All
Well,
right.
thank you both so much. Amazing presentation, and thank you to all of our attendees for joining us today. It is such an honor to be along this ride with you. So thank you.
Thanks, guys. We really appreciate you showing up tonight.
Yep. All right. Bye, y'all.